It's a pleasure to introduce Martinez from TAMU. She's the director of the Center for Global Assisted Search and Rescue, and she's going to talk to us about that interesting topic.
Okay, it should be on. Howdy.
Howdy.
And it's nice to not have a robot disaster. It's good just to have a standard AV type of problem. And thank you very much for having me speak with such a great group of people today. Usually I talk about a specific disaster. And like any field work, it also raises questions of, what are the generalizable lessons that would apply to your work? What's the quantitativeness of it? And often there's not, because they're one-off events. So today I'm going to talk about the metrics that we've been learning and we've developed and what we think they indicate for new platforms and simulators. So trying to generate and think about how to take these field experiences and make them more quantitative. And there we go. So I would like to give a big shout out to my grad students. This work, everything that we do is really powered by the grad students and our industry partners with Robotics Without Borders. And work you get will be from, most of this is in my new book on disaster robotics, but also from some recent work that you read, some work that Sid Argawal, he may be here, has done along with Julie Adams. So when we think about the motivation for the course, we think about UGVs and disasters. The question I get is, hey, look, this has happened, what robot to use? And the ground robots, there's so many different sizes, so many different types. How do you figure out what's going on? And then how would you know it moves inside of that? And now we're beginning to use UAVs indoors, talk about them. Vijay Kumar used some at the Tohoku University, one of the damaged buildings there. So these are coming in a possibility. And again, the same question. How do you know fly in there? How do you know how big it is? And so how do we get that? And that's something we think about these disasters as they happen. We'd like to use them. So what could we do if we could somehow quantify what's going on? What were some of the things that we might be able to do? Well, of course, one of the advantages is that you can compare performance, right? You can say, well, they were at this incident and they had that, and notice that we can generalize. Or we can say, well, they didn't do this and that. But some fun things we can also do is that, like the question I have, how can we predict what robot is going to be suitable for a particular application? And what does that tell us about our computer-based simulations? Are we simulating the right things so that when we actually try it in the field, they'll be successful? And what does that say also about our stage worlds when we fly indoors and we set up our props and we try to make it look realistic? What is realistic? What are the heart of realism for this? Well, what we've converged on is we think that two key factors in quantifying the environment or the operational envelope for an unmanned system are going to be scale and traversability. Scale, how big it is, and how maneuverable can you be in that environment. So let's go with scale first. Or perhaps not. There we go. All right, so think of scale. So if you're from an engineering background, you know what a dimensionless number is. It's like the Reynolds number, is that once you get up to a certain flow, all of a sudden you're going from laminar to turbulent flow, things like that. So can we come up with these scalable numbers that tell us something that we don't have to know everything and recompute for every single robot? So looking at the idea of scale, is there a way that we can say if we know something about the size of the environment, and we know something about the size of the agent, would that tell us how they fit? And so scale as a dimensionless number, so we start out thinking about the agent. And part of this we're going to call agent both from the AI background and from the idea that we're going to see similarities between how humans move and robots move, so it's an easy analogy to make. So think of that people have a characteristic dimension when it comes around being in space. Okay, so people in space, and we see this, a confined space for search and rescue or for occupational safety means that you're in a space that you can't turn around in. You have to crawl back out, which you can think of for worker safety is bad because you're not going to crawl out nearly as fast as you crawled in. So it's about it. So usually it's about twice the width of your shoulders is the characteristic dimension. If you've got a space that wide, you can usually work your way around and get around and crawl back out. So that's usually a confined space. So if you think about that, it turns out to be about the same with robots. Now most of these robots are just very small and not the most commonly of the rescue robots used, disaster robots. Something like a Patlock is bigger, and it's about our size in terms of shoulder width. And these robots can all go backward. Well, not so much, but some are built to drive backwards. But it turns out in terms of maneuverability and stuff, using that radius of being able to turn, how much does it take to turn in place is a good idea. And if you think about an unmanned aerial vehicle, something like a quad rotor, not so, the turn in place doesn't really count so much, but you think of it as what's the minimum space you would really trust it to work in? So what's the tolerance on its size and what drift you might have, and that tells you the space that you need to get in. So once you have that, you have the agent space. Now let's talk about the environment's characteristic dimensions. So what does that mean? And we've defined that over the years, starting right before the World Trade Center, as thinking about it in terms of the cross-section of the smallest opening you're likely to encounter. So if you look at this, the smallest opening here, this is from the Cologne, Germany, the archive collapse, that's pretty darn small. Whereas if you're looking at perhaps flying inside a building, that's pretty darn large in comparison. So how do we start explaining that? Well, that's where that idea of a ratio comes in. So if we think about being habitable or outdoors, those are environments where the ratio is greater than 1, that the environment's very big compared to that robot's characteristic dimension. And usually for ground robots, it's about that 2. If it's greater than 2, we can turn place. That's really nice. And if it's greater than that, it's almost the same practically as being outdoors, even if we're indoors. Now, what gets more interesting for the work I do, because typically I get all the nasty stuff, is if people could do it, you wouldn't need a robot and have to call somebody in. We start looking at what we call the confined space, or what, from an engineering perspective, a restricted maneuverability space. That's where our ratio is about 1. We're about the size of the robot. The robot can't really turn around in that space. So that's tough. And we also see that it's about the ratio of 2 for a person, normally that they could fit in and not be confined space, but if they have to put on any hazardous materials, protective equipment, then they immediately have reduced maneuverability just in terms of space. And if you've ever worn a level A or level B suit, you have all sorts of other problems. But just in terms of the space it takes it. So for instance, if you have a train wreck or a chemical train spill, of which there are about 700 a year that are reported, who knew it was that many in the United States? They have to go look. If they can't find the engineer, they've got to go see who's up there. So you have to don the suit, try to get up in that cab without falling over, without tearing that tie back, that very thin plastic suit yourself. So they're less than thrilled. Anyway, confined space. You can maneuver, but it's going to be slower, going to be much more challenging, just on a physical part. And then there's a space here we call granular, where the environment is actually smaller than the robot. This is the big win as you think about things like mudslides, avalanches, these mixed rubble, sand, where you can dig down, you can burrow down quickly, you can really do a lot of life saving there. And these are some pictures of animals do that. The sand lizard that you see, working with Dan Goldman from Georgia Tech and Howie Choseth with an NRI grant on looking at these types of robots for role. So we put this together. You can kind of think of this going from really hard to really easy in terms of environmental spaces. The granular for a robot, it's, the environment's smaller than it is. It's a maneuverability. That's hard. That's red. And then as we go out to the habitable areas where people can maneuver around, it's got lots of space, we're going to put that as green. And so we see that. All right, so now so that idea of a dimensionless ratio kind of gives us a clue about that. And now I can also, if I know the environment, I can kind of make a guess as which size of which robot versus the size of the environment you're expecting to work in. All right, traversability. So So let's look at that. That was the second thing, so scale traversability. So what does make, how well a robot can maneuver around? Well, the things that help it maneuver around, if you think again, is like going from red to green, tortuosity, that's a term from animal behavior about how many turns you have to make. So the more turns you have to make, the harder it is, right? That means it's a more difficult environment. So the better, the less tortuosity, the higher, the lower tortuosity is better. Verticality, a lot of times we have to deal with vertical drops, particularly with rubble. You're actually on the roof or what's left and trying to get the robot down. So that's a challenge usually. Favorable surface properties. We all know about the difference between going on carpet and smooth surfaces between heat, mud. Severity of obstacles and the number of doors and things that you have to go through all of those. But of these, one that's really interesting and has the most impact we feel is tortuosity. This one here is the idea of tortuosity. How many turns? So it's from animal behavior. The animal behavior people have measured how animals predict, create their paths. They've actually used it for Alzheimer's patients. When the tortuosity goes up, when they just normally are walking around their house, people typically do very smooth paths, very straight lines. Once the Alzheimer's kicks in, they actually start making lots of turns, just kind of wandering. Even though they make it over to there, you can track and see. And that turns out to have a higher fractal value, which is really just the number of turns per distance. We've seen that it's called fractal D. Marty Boschel, one of Dave Wood's students at Ohio State, did this for RoboCup Rescue. Jeff Craig, one of my students, did this at USF for his thesis. And so it's a nice measure. So just to see this in a UAS, because it's just easier to visualize a UAS turning around more than it is, like, okay, imagine this thing you can't see when you see underground robots. But here, think of this as the number of turns. So it goes the turns this way and up and down, and how the UAV would have to go through that. And in this case, it has a tortuosity of 5 because it had 3 turns over 6 meters. And so here, one of the reasons, the disaster city here at Texas A&M, about 5.5 miles that away, is my favorite place on earth because it's got all of these facilities for training emergency responders, all types of urban collapses. And one is a big building, urban multi-story commercial building. So here's what the responders consider an easy, canonical indoor environment after a bombing, like the Oklahoma City bombing, or after a hurricane. If they got called in, here's what they can expect. Look at all the stuff hanging down. Look how irregular it is. And so the tortuosity there, this particular building, is about 1 turn per meter. Right? So it's pretty high. But still, so you go a meter, you either got to go up, down, over, or something. You just can't, like here, we have like a tortuosity of about nothing, right? Because if you stay above our heads, they're in below the projectors, you're good. But here you've got almost all UAVs that fly indoor are about the same height, same characteristic dimension. So that's the idea behind tortuosity. So now let's try to see what happens when we put scale and traversability together. Does that give us any additional power in thinking about what we're learning about how to generalize field work to what we can do there? Well, you remember that, right? Going from there, the increasing scale, the ratio. And then we've got, remember the traversability? Well, if you just think about flipping that over, so there, and you put those together, now they're orthogonal, right? So you've got your scale this way, you've got your tortuosity that way, red is bad, green is good. Well, one of the things you can see is now think about that in terms of representative environments. What are the environments where robots have been used at? Okay, so over here, where you've got basically a dormitory that still looks like a dormitory, this is a lot like Fukushima, Daiichi. The building was still largely intact. The problem was the hazardous radiation with there, and so people could have gotten in there, but so you've got a big space. You can use bigger robots there. Over here, you've got areas that's much more of a pancake collapse. You're beginning to get into spaces where a person couldn't get into, and it's very, very, and if you go to smaller robots, it's even harder for small robots. It's still, the ratio is still very small. And then you get down in here where you're trying to go into things that are your size or even smaller. What gets, for us, that's nice because now, like I said, you can say, well, these are the big robots areas. These are the smaller robots. These are the ones that, the smallest ones that you can rappel down, because a lot of this has got to do with 3Ds, going from the top down. And then here you start seeing a region that's pretty good for, you know, the packbot size robots. They're not too big, they're not too small. So that helps me. Something like this helps me tell people what robots to use for a disaster. But for us as researchers, it also gives us a clue about the future. And one of the things about the future is where are the gaps? If you were going to build a new platform, where would it be? Well, here is that these two areas aren't that particularly interesting. Here you're competing with humans, okay? So the only times, unless it's super hazardous material in a very short time period, then this is the only way robots can get used, because people can get in there pretty easily. Here, people have trouble. They may be wearing so much protective gear or the size that are going to be in here, but it's still possible for them to get in there. And that means they've got to be at least as fast. They've got to be break even or slightly better than a human, because what's the benefit of having a robot if you could do it? And originally in bomb squads, that was a huge problem. They had the big old Androses that were built for the nuclear industry. They were sumo, that. And they would just eventually turn them off, put on the shielding, and go downrange and defuse the bomb themselves. It's only when they got smaller, like the packbot style, that lighter, easier to use, did they actually begin to have a cost benefit that was favorable. But down here in the red, the smaller, the more granular, the smaller the scale of the environment, there's no other option than to use a robot. And we don't have a lot of robots down in that range, of that scale with these types of environments. And so I think that's telling us that's where we need to concentrate more on. This work also, these idea of metrics also help us think a little bit more about realistic simulators. So as we start thinking about indoor flying, Sid went back and did a study of 12 unmanned aerial systems that were either simulated or flown indoors. 83% of them, and which was 75% of the urban search and rescue, the ones saying, oh, we are building this specifically to fly indoor for disaster, were all at that habitable scale. The scale was so large compared to the size of the robot. And yet all the robots are about this big. So there's not really much advantage of using them. They're not testing it in environments that you would actually need a UAV for. You're testing in environments that you needed that information really badly enough, somebody would have gone on and gotten it. So we're not, you know, of course we're all beginners as we get into unmanned indoor environments. But thinking about that, we're not pushing, we may not be pushing as hard as we should be, because we need to at least be working with strength and mobility, maneuverability scale. And then also notice that the tortuosity was well under 60% of what a realistic tortuosity is, if you're going to fly for a disaster. If you're going to fly for doing a selfie in a large area, that's different. Let's say that. So it lets us start quantifying, are we getting the right things in our simulators, depending on what we're looking for. So in summary, you know, fieldwork is often considered irreproducible, just one-off case studies, of which is very hard to generalize information or compare what's going on, who did what. So what we've tried to do is start and have been working on and offer some metrics, and in this case, metrics for scale and tortuosity. And we believe these lead to predicting the suitability of an unmanned system for a particular environment, and also predicting what the next generation platform should be. Smaller is better. You know, really look at that. Gene's work is really nice, looking at those types of things. And then more realistic simulators to make sure we're not in simulation, easing out the problem, assuming our way out of the problem, and then we try it in the field, it doesn't work. So I think that puts us back on track.
So, are there any questions? I have question. So why are they that much? They're performing almost small enough for these applications, maybe.
Well, why are robots large or small regardless, right? So you've got the size of the battery, you've got whether you're doing an onboard battery. The smaller the robots typically have their batteries run through a tether. A lot of companies don't like to make tethered robots because they're scared the tether will tangle. Although our work has shown that it's 50-50 either way. For every tangle you get, you get the ability to pull it back or actually use it to actively help. If you're using it for disaster, which again has usually high verticality, you're going to go up and down and around. So the tether actually is used as a belay line. So there's different trade-off in sizes. If you're doing IED robotics for Afghanistan, you don't need to engineer something small. You need something bigger that can carry an arm, that can do things. So it's a design constraint.
Can you comment on sensory requirements? What kind of sensors are useful in the product?
Yeah, it's all over the map. You always have a camera, right? Cameras are always good. Thermal is always nice. It's nice to have. If you only got one, you've got to have a camera. 2 cameras are good. Range is an interesting one because often in the highly tortuous areas with the high turns, you don't get more than 8 feet ahead. So often you've only got 2 or 3 feet ahead that you could actually see anyway. So some of these longer, more expensive, more power-consuming lasers don't really get you anything because they're really optimized for longer distances than we actually see the need, perceive, no pun intended, see the need for. So we'd love to have better ranging, we'd love to have better probably the bigger thing is to have better post-processing, real-time post-processing, better equalization, better zoom, better depth, better, and we still see it's very primitive. It's like, look, just, make it easy to link into OpenCV and we'll just take it from there, type of things. So I don't know that we need so much new sensors, so much as we need to exploit the sensors we have and do more processing.
Is there any work with swarm-type robots for the real small spaces that might communicate with each other for search and rescue?
There are many people that are looking at swarm-type robots or postulating that work that. We've never seen any of them actually work, and we believe there's going to be significant problems, okay? And I am so not trying to diss anybody, dissuade anybody from working in that area. But a multi-story building collapse, there is a tremendous amount of metal in any of those buildings that interferes with wireless connectivity. And the way you get around it is that you have lots more power, unless you assume all the robots are very close to each other. One of the first things I learned in going to the field is that these voids, even ones these big, are very rare, and they usually don't go all the way. So really, I think the bigger win is to work on the ones that can go deeper and burrow, rather than worry so much about having lots of them. We're just not seeing the large number of voids. We're not seeing the wireless connectivity is going to be enough. And search and rescue is not we found somebody. Yay, we're giving one bit of information back. They don't send the robot in until they think there's somebody there. They run through, the procedure is to run the dogs through. The dog gets a hit, says somebody's here, which is great. In a building, is the airflow. So the dog can be here saying, yes, here, 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 and the person could be way over there. And the dogs are trained to go around and they kind of do their own little global optimization. Then you bring in a second dog. And only at that point do you say, okay, we got something. Because that also means you're bringing in the rescue crew. You're bringing another group of resources, stop what they're doing to come over to do a live save. And at that point, you bring in the robot to try to say, is this the shortest path? Can I start bringing out the structural engineers immediately want to see what the robot is able to see? Because it's like pickup sticks, am I going to, if the way we dig down to get to the person is going to kill them with a secondary collapse, you've got the medical people trying to figure out what's going on, you've got the person who's running the thing. So it turns out the one bit, we already got that from the dog. we already knew from reports, there is a person in this place somewhere. This is the only place you need. So we actually don't need to find a person per se. We need to see. We need the responders. Several of them with different skill sets need to be able to project themselves into that environment and see. So it's sort of a